Coincidence? Here are 3 examples for you to think about. You changed your study method, your grade went up. A company ran ads, sales went up. A new drug was tested, patients improved. Was that real, or was it just luck? One number answers all 3 questions, the p-value. And by the end of this video, you'll know exactly how to use it. Quick question. Pause and actually think about this. You flip a coin 5 times. You get 5 heads in a row. Fair coin or something off? Most people's gut says, probably not fair, something feels wrong. But how do you prove it? How do you go from a feeling to a real conclusion? That's exactly what hypothesis testing does. It turns your gut feeling into a number.
Here's the best analogy in all of statistics. Once you see it, you won't forget it.
Imagine you're a judge. Someone stands in front of you accused of a crime. Before you see any evidence, any witnesses, any documents, your starting assumption is clear. Innocent until proven guilty. That isn't just a legal phrase, it's a logical framework. You start with a default. Evidence has to be strong enough to overturn it. Weak evidence, you stick with innocent. Strong evidence, you change your verdict. Statistics works exactly the same way. In a courtroom, the person is assumed innocent. That's your default. In statistics, the null hypothesis is your default. It says there is no effect, nothing is happening. In a courtroom, the prosecutor argues guilty. They're challenging the default. In statistics, the alternative hypothesis challenges the default. It says something is happening. There is a real effect. In a courtroom, the judge examines the evidence. In statistics, we collect data and calculate how strong our evidence is. Strong evidence in court? Guilty. We change the verdict. Strong evidence in statistics? We reject the null hypothesis. But here's the part most people miss. Weak evidence in court doesn't mean innocent. It means not guilty, not enough proof to convict. Weak evidence in statistics? We fail to reject the null hypothesis. We do not say the null is true. We say we didn't find enough evidence against it. Not guilty is not the same as innocent. Fail to reject is not the same as the null is true. Hold on to that distinction. It matters. Let's make this real. A school introduces a new teaching method. Test scores go up slightly. The principal is excited. But the statistics teacher asks the uncomfortable question. Is that improvement real or just random variation in scores that would have happened anyway? The null hypothesis says the new method has no effect. Any improvement is just luck. The alternative says the method genuinely improves scores. We collect data, we run the numbers. Now we need one thing, a way to measure how strong our evidence is. Here's the clearest definition you'll hear. If the null hypothesis were true, if there were genuinely no effect at all, how likely is it that we would see a result as extreme as the one we got just by random chance? Read that again in your head. That is the entire definition.
Let's go back to our coin. 10 heads in a row. If the coin is fair, if the null is true, the probability of 10 heads is roughly 0.001, less than 1/10 of 1%. That is a tiny p-value. It means this result would be almost impossible if the coin were truly fair. So we have two choices. Either something incredibly rare happened by luck, or the coin is not fair. The p-value does not tell you which one is true. It tells you how surprising your result is, assuming nothing unusual is going on. Small p-value, surprising result. Hard to explain by luck alone. Large p-value, unsurprising result. Could easily happen by chance.
Good question, but how small is small enough? This is where researchers make a deliberate choice before they even look at the data. We set a threshold. It's called alpha, the significance level. The most widely used threshold in economics, business, and medicine is 5%. That means we're willing to accept a 5% chance of wrongly rejecting the null when it's actually true. Think of it as our standard for reasonable doubt. The decision rule is simple. P-value below 5%, reject the null. Statistically significant, the result is unlikely to be random. P-value above 5%, fail to reject. Not enough evidence, could be random. That scale is one of the most important pictures in statistics. Remember it. Okay, your turn. I want you to pause for 3 seconds and make the call yourself. This exact question shows up on every business statistics exam. The school ran the study. P-value equals 0.02. Is 0.02 less than 0.05? Yes, so we reject the null hypothesis. The improvement is statistically significant. It's unlikely to be random chance. The school has evidence the new method works. Now try this one. P-value equals 0.38. 0.38 is way above 0.05. We fail to reject the null. We cannot conclude the teaching method made a real difference. This result could easily be random variation. And here's the important line, the one most students miss on exams and most analysts mess up in reports. We do not say the teaching method does not work. We say we did not find enough evidence that it works. Those are completely different statements. One closes the door, the other says, come back with more data. Let me show you 3 mistakes almost everyone makes. Mistake 1. Failing to reject the null means the null is true. Wrong. It means you didn't find enough evidence. The effect might still be real. You may just need more data, a bigger sample, or a better study design. Not guilty does not mean innocent. Mistake 2. The p-value is the probability that the null hypothesis is true. Wrong. The p-value is the probability of getting your data if the null were true. Completely different. This is one of the most common errors even among professionals. Mix these up on an exam and you lose marks immediately. Mistake 3. Statistical significance means the result is important. Wrong. A result can be statistically significant but practically worthless. A new policy that raises average income by 50 cents per year might be significant with a large enough data set, but who cares? Always ask, is this effect large enough to actually matter in the real world? Statistical significance and practical importance are not the same thing. Let's close where we started with the courtroom. Null hypothesis, your starting assumption, no effect. Innocent until proven otherwise. Alternative hypothesis, the challenge, something is happening, the prosecution's case. P-value, your measure of evidence. How surprising is this result if the null were actually true? Alpha, usually 0.05, your threshold for reasonable doubt. P below 0.05, reject the null, significant, real enough to act on. P above 0.05, fail to reject, not enough evidence, we stay with the default. One number, one threshold, one decision rule. That is all hypothesis testing is.
Before we wrap up, here's a check your understanding question. Pause the video and think through this yourself. Here's the answer.
1. We fail to reject the null hypothesis. 0.12 is greater than 0.05. We do not have enough evidence. 2. In plain English, we cannot conclude the diet pill works. The weight loss we observed could easily be random chance. And remember, we do not say the pill doesn't work. We say we didn't find enough proof that it does. Those are completely different statements. If you got both right, great work. In our next video, we're going to look at how economists actually use regression in the real world. If this video helped, like and subscribe. Drop a comment. What confused you most about p-values before watching this? I read every single one. New lessons every week. Simple, clear, to the point. See you in the next video.